Hello everyone, hope everyone is doing well. Today we're going to talk about hypothesis testing and we're going to see what it does and how it can help us answer different statistical questions. So we always have been talking about in statistics thus far is that we would like to know about the population, let's say population mean or population median or some statistics of the population. However, it is very difficult to collect all the data from every single entity in a population. So the population may be very large or may be very difficult to get a hold of to collect information. So instead, what we do is we may have to just collect samples and try to figure out how the sample looks like, and then from that we can kind of get some information about the population. So instead what we do is we collect some sample from a population and then study its characteristics. So let's say if I have a school with a population of 10,000, it may be very difficult for me to get all their information, so I may just get a sample of maybe 100. And from that, I may try to find out what is, let's say, the average GPA or whether students mainly live on campus or off campus and other information. So before we start, like one thing we do in economics and in other fields and in statistics is that we first come up with a question before we start our experiment or before we start our collecting our sample. So we may start with an idea, then that question is converted into something that we call a hypothesis. And finally, with that hypothesis, we collect data and then we test the hypothesis to see if it's somewhat, we won't use the words correct or not correct. We will say if we can reject the hypothesis or not reject the hypothesis. So what are the steps of any kind of data collection and analysis that we do is first, even before we collect data or something, we first have to realize what are we doing? What are we trying to collect? So the first step is we come up with a hypothesis. So we come up with a hypothesis, we try to figure out what this hypothesis is about. The second step is then, based on the hypothesis, we collect the data. So after we collect the data, and then based on our analysis, we will see, we will see in a bit what do we mean by this statement. Do we reject the null hypothesis or not? So when we look at step one, let's say we're talking about step one where we come up with a hypothesis. A hypothesis is usually broken down into two sentences. So the first sentence is called the null hypothesis, and the second one is alternate hypothesis. So in the first step, when we're talking about we come up with a hypothesis, basically we come up with these two sentences. So this is going to be my step one. Now, what is null hypothesis and alternate hypothesis? It's easier to understand it through, let's say, an example. Now, let's say that in our case, maybe we are talking about colleges and we hear that in colleges, there is this whole debate going on that there's such a thing called grade inflation, and courses are giving out A's and B's a lot more than C's and D's compared to previous years. So maybe we want to test is grade inflation a real thing? Which means are grades getting higher and higher over the years? So the null hypothesis is usually just like in when we put someone in trial. Null hypothesis is basically the statement is innocent or null. Or basically, if you think about it, it's like you're innocent until you're proven guilty. So in our case, let's say the null hypothesis. Now, in some places, we also write it as HO. So it is also written as HO, and the O is sometimes in lowercase, like that. The alternate hypothesis is sometimes written as H1. So we write it as H1. So in that case, we will say that, is grade inflation a real thing? We have to first, this is my question, this is the thing I want to study. The null hypothesis is going to be, there is no grade inflation. That is, whatever we have, the status quo remains, that no, there is no grade inflation. And the alternate is, there is grade inflation. So with our null hypothesis, we basically have to disprove the null hypothesis, or this statement. That is, the status quo is the person is innocent, or the statement is not valid, it does not exist, and the alternate is, it is, or it exists. So another thing to note that here, after we get this done, we are now going to collect the data. So we are going to collect some data. Let's say we collect n equals 100, as we said. And we get some mean and standard deviation. And then we try to collect, maybe we have some prior information about what was the average GPA in prior years, and then we can test using that. But one thing to note here is that even if we're collecting the data of a sample, and we're using the sample to test what the population is doing, the null hypothesis is never of this sample. Even though we're using the sample to get information to reject or not reject the null hypothesis, we are actually testing for the population. So instead of saying, let's say we could say there is no grade inflation in the sample, if we write that, that is incorrect. So we should never write that. We should write in the population, because we're testing it for the population. And then there is we could write evidence of grade inflation in the population. So we could write it this way too. Now in a few minutes, when we will be looking at some exercises, we can also see how the null and alternate hypothesis can be written in mathematical form. We don't have to write sentences like this, but either way is fine. But one important thing is to notice is that null hypothesis is always testing the population, not the sample. Supposing if I were to test, let's say, just showing another example, let's say I want us to look at, say, the average. Let's say we are looking at this statement. Let's say there's some population, and in the prior years, the population mean was 50. So if you remember from previous times, we denoted that mean, if it's of the population, we denote it as mu, and so mu is 50. Now we can't collect the data of all the members in the population, but we have a sample. Let's say sample is of a given size, and this average is now 53. So x bar is 53. And now if we were to say test this, so if we were to write a null hypothesis and alternate hypothesis like this, then we could write, if I write null hypothesis, we could write the population mean is 50, and the population, alternate is population mean has increased, okay? Or we could have tested the average. Let's say, has it decreased? Maybe the average of the sample fell to 47. Has it decreased? Or we could also test, has it changed? Which means it could have increased or decreased. So that means the alternate would be different. If I were to write it in, let's say, in notation form instead of in sentences, I could also write H naught would be mu equal 50, which is telling me that the null hypothesis means that the population mean is 50, and the alternate would be that mu is greater than, or let's say if I wanted to test if, let's say, just to keep it easier, let's say it has changed. which mean that has it increased or decreased? So in that case, we would say mu is not equal to 50. And notice that here we are not using the notation x bar because we are not using this sample to study this sample. We are using this sample to study the population that we have right here. Okay, so after we collect, and later in the lecture, we're going to see how do we analyze this data. And then after that, we're going to say that, let's say if we test the null hypothesis and the null hypothesis, we never say we prove or disprove the null hypothesis because we can always have errors in our, maybe in our methods of data collection, or maybe we did not sample it properly. So we will always say that we either reject the null hypothesis or not reject the null hypothesis. Now, even after that, let's say, supposing there are cases where, let's say my average, the population average is 50. And let's say it has actually remained 50. Now, if you remember, we talked about how the sample, when we have a distribution like this, maybe this is my mean. However, what I ended up doing is that when I collected the sample, I collected, let's say, 60 individuals, I only collected people maybe from this range. So maybe I just somehow, even though I may have tried to randomly collect it, but I may have just collected people who are in this range. And now, all these people the values are less than 50. So maybe my X bar, the sample average, is 45. And supposing after I test, I find out that yes, it is, X bar is 45. So I say that, in my case, then I reject the null hypothesis because I find after collecting all the tests and doing the right kind of test that the population mean is actually 45. But in fact, I did not sample properly. The population mean has remained at 50. It has not changed. So in that case, we have two kinds of error that we may face. So one is called a type 1 error. Type 1 error is when we reject a null hypothesis when, in fact, it is true. So type 1 error is telling us we're making something like this. We have collected a sample which has a lower sample average or a much higher sample average. Maybe I collected a sample and it is way up here where X bar equals 55. And I tested and I found out that no, this actually is true. But if I actually had the information of the whole distribution, I would have noticed that no, it is not true. So in that case, we are actually committing something called a type 1 error. Now, another kind of error is called a type 2 error. Type 2 error is when we actually fail to reject a false null hypothesis. Or in other words, we can say we do not reject a null hypothesis when it is false. So we're saying that the null hypothesis is wrong, basically. Let's say that actually the mean did change. It moved over to 55, but we ended up doing a test and it shows us that no, this is the true mean has remained at 50. And that's where we commit what we call a type 2 error. So, and these two errors are always going to be there, one or the other. If one increases, the other one decreases. So we just have to keep them in mind. And that's one reason why it's a good idea is to do repeated tests, is to keep on repeatedly sampling from the population so that we may not run into these type of errors. But it can be very difficult to completely eliminate type 1 and type 2 errors. Okay, now let's go into, so we talked about How do we come up with a hypothesis? We are going to somewhat skip how we collect data because we have to make sure we collect data in a way so that we try to reduce the possibilities of type 1 and type 2 error. That's a whole different field. We will just assume we have the data. Now let's analyze the data. So as we said that, let's look at our example here again. If mu is 50, so if mu is 50, and this is what we are testing, and our alternate, maybe we want to test that, has mu changed over time? So mu is not equal to 50, as we have written here. Let's say it has, the population mean has changed. So we are now testing this. Now, in this case, if this is my mu, as we have seen in a previous lecture in normal distribution and in other continuous distribution, getting a mean at exactly this value is very low. So, and even when we looked at central limit theorem and all that, is that landing, if I take a sample, so my n is 60 and I get a certain x bar, the x bar, the probability that x bar will exactly equal to the mu every time is very low. So we may get mu, we may not get mu. So we may get some, maybe an x bar may be here, an x bar may be here, or maybe here, or maybe here. So we think that, okay, there may be a certain range between which we will say that, okay, that x bar, even though let's say the x bar is 48, that is still close to 50, so we may consider this that, yeah, I know the x bar is 48, but it's not that different from 50, so we will say that the population mean has not changed much. So we try to keep, we say that, within a certain range, this mean will say we will hold. So if my sample average is within a certain range, let's say between this range and this range, then I will say, okay, well, yeah, we should still assume that the population mean has not changed. But beyond these two numbers, so let's say if I go here or here, then we will assume that, yes, definitely, my population mean has changed. So then we have to determine what are these two boundaries, what are these two thresholds. How do we determine what this threshold is? So in our testing, when we test one sample test or two sample tests that we will look in a bit, we're going to figure out how do we determine this threshold, and then we're going to figure out if then a number falls within this these two bounds. We will say that, okay, well, this number is close to the population mean, so we will say that the sample and the population mean are not very different, so then the population mean remains at 50. Now let's say if the sample mean is at 37, or let's say the sample mean is at 65, that means that this number is so far away that we will say that it's kind of unlikely that we may get something this far away if the true mean is 50. So then we will say this number is probably the new population mean. Or this number, if it's way far up here, is probably the new population mean, because the probability of getting this is very low. So from here we can then say that I will basically then calculate the probabilities. If I am looking at a distribution, this is my null hypothesis, and I'm testing if mu equals 50, then, and the alternate is mu has changed, so mu is not equal to 50, then I will say, okay, well, I want to be, I'm thinking that if I collect the data, and also looking at, if you think about central limit theorem, maybe 90% of the data I know should be within a certain range. 95% of the data may be within a certain range, let's say a little higher, or 99% of the data should be within a certain range. So outside of that range, we would call them outliers for our case. That is telling us that the number or the collected sample mean may be very different. So we can choose these numbers, and these are then our thresholds. So if I want to make sure that, and in many cases we use 95%. So if I want to say that I understand that if I take a sample from the population, 95% of the mean should lie between these two numbers. And these two numbers are still to be determined. And 5% of the numbers should lie outside of that. So since it's on either side, we will say 2.5% may lie on this side, 2.5% may lie on this side. And so therefore, if I know that mean is 50 and 95%, if this was the true mean, then 95% of the sample averages should lie between these two numbers. And if they lie outside of those numbers, here or here, then we will say that, okay, well, the chance of that is very low. It's 5%. So if we are actually seeing that happen, that means that maybe the population mean has changed. And so we would say then, maybe it has changed to not exactly maybe that number, but maybe it has moved. If it has lower, then maybe it has moved to the left. And so we would then say that there is evidence that this null hypothesis that we have talked about, that the population mean is 50, this is no longer true. We may have to say that, but we don't say that it is no longer true or false. We will say that we may reject this null hypothesis, and or we may say that the null hypothesis has are not rejected or rejected. All right, so let's look at an example of a null hypothesis testing and testing the null, or whether we reject or not reject the null, and how do we frame a question like that, and or how do we frame a hypothesis like that, and then how do we test it. So let's look at this example. Average time in a 100-meter dash race in previous meet is 13.4 seconds. Then in the current meet, we have 50 participants participating in a race, and the mean time is 11.5 seconds, and the standard deviation is 1.8 seconds. Test if the average time in the current meet is different from the average time of the previous meet. So this is telling us that we know from here the average time in a previous race is 13.4 seconds, so this number must be my mu. And so in a current meet, we have n is 50, erase that, n is 50, and the average was 11.5 seconds, which is my x bar. And I have a standard deviation of this x bar, or basically from this 50, so this is going to be my s bar. So now we have to test if the average time is different from the population mean. So in this case, first, step 1, let's come up with the hypothesis. So we first write the null. I'll write H0. That's the null hypothesis. And the 0 is usually a little smaller, so we'll write it that way. And in this case, I will write it in both ways so we can see how they are similar or different. So the population mean is 13.4 seconds. And the alternate is, we will say, since it's asking us that, is this number different? So different means, or is this number changing? That means that it could be either greater than 13.4 seconds or less than 13.4 seconds. So we would say the population mean is not 13.4 seconds. Okay. So this is one way we could write the hypothesis. The other way would be, basically we would have the same notation for null and alternate, but we would write to insert some symbols here. Let's say, so the null would be mu equals 13.4, the sign here, seconds, and the alternate is mu is not equal to 13.4 seconds. So this, we could write it either this way, or we could write it either this way. Either way is fine. They basically mean the same thing. So that was why step 1, I come up with the hypothesis, and then at step 2 is I collect the data. So I collected the data. My n is 50. My x bar is, as I wrote, 11.5 seconds, and my s bar is 1.8 seconds. So now we have to test is this number, this x bar, any different from the population mean that we have seen in previous meets. Now, how do we do this test? So we're going to do a sidebar here, and we're going to look at tests given 2 scenarios. So the test will be, one of the tests is if the population standard deviation is known. And the second test is if the population standard deviation is not known. So if the population standard deviation is known, we would use something called, we would use the normal, we would use the normal distribution, and we would use the normal distribution in this case if the population standard deviation is known. So we would say we are going to use the normal distribution. And if the population standard deviation is not known, then we would use the t-distribution. So in our case, let's say that if I go, in our case here, we don't have the population standard deviation. It's missing. We have just the sample standard deviation. So according to this, we should only use the t-distribution. Okay, so we are going to write here so we are going to use the t-distribution. Now, step 3 would be analyze the data. So in our case, if you remember back what we talked about in a couple of minutes ago, is that, again, we're going to do a sidebar, is we said that, okay, we are going to have, if let's say our population mean was truly 13.4 seconds, right? It was 13.4 seconds. So if it were truly 13.4 seconds, then what would happen is, if I were to, let's say, use central limit theorem and repeatedly do this sampling and testing, I could find out that 95% of the time, or 99% of the time, or 90% of the time, let's just use 95% of the time as an example, that the sample means would lie within these 2 certain thresholds. So 95% of the time, the thresholds would lie between certain numbers, some seconds here and some seconds here. Now, we don't know exactly what they are, but what we could do is we could convert this number into a z-value or a t-value. So we could convert this whole distribution that we have into a t-distribution, because we don't know the population standard deviation, so we're using the t-distribution. And how do we do that? So we convert the threshold values into our t-distribution. So in our case then, we would then rewrite this as, this is going to be centered around 0, and 95% of the time, this t-value would be equal to t dot inv dot 2t, or let's actually just use inv. So my probability is going to be 0.05 divided by 2, because 95% of the time it's going to be here, and 2.5% of the time will be on each side. And the degrees of freedom, I think we said we had n is 60, minus 1. I still have to go and check what n is. n is 50 actually. So n is going to be 50 minus 1. So then my lower bound or lower limit is going to be negative 2.009. So this number will be that. So even though I may not know exactly what the actual 95% level is, I could probably find it if I knew the population standard deviation, but I don't know that. But what I can do is I can convert the distribution I have into the t distribution and use this value as my lower bound. Then my upper bound would be, since it's a symmetric distribution, it would be the same thing. So I would write equals to t.inv, probability 0.05 divided by 2, degrees of freedom is 50 minus 1. And if you're unsure why we are doing this, I have a video on confidence intervals, and you can check that out to understand why we subtract 1 from that, what is degrees of freedom. So I'm not going to go over them here. And since it's on the right-hand side, we'll just put a negative value here. So we get a negative, so basically a positive number. So if you notice that if I convert the distribution into a t-value, my lower limit is going to be negative 2.009. My upper limit is going to be positive 2.009. So if I calculate therefore my t-value, if it's within this two thresholds, I should be fine. So if, let's say, the t-stat that I calculate, and we are yet to figure out what is that t-stat, let's say the t-stat is 1, that means it ends up here. It is within this threshold, so we can't say that, okay, well, I know that 95% of the time, if the mean was 50 or 13.4, the sample means should be within this 2 threshold. So we cannot really reject that the population mean has changed. However, if my t-stat ends up going to, let's say, 2.5, then we are way out here. Now, we said 95% of the time it would be within this 2 range. If it's way out here, that means there's a pretty big likelihood that the population mean has changed. So let's find that out. So we go here now, we analyze the data. The way we calculate it, we figure out whether this number is different from the population mean is, since we converted everything to a t-value, we should also convert our sample numbers into a t-value. So if you remember what the formula of the t-value is, or how do we get our t-values, we get them and we will call them t-stat. So the formula for my t-stat is this number, x bar minus mu. We find that, and then we divide s bar with divided by the square root of n, and we call this number, the bottom part, this number is called the standard error. So we will calculate that. So let's first look at that. I'll write it. First do the numerator first. So x bar minus mu is going to be 11.5 minus 13.4, which comes out to be negative 1.9. And then the denominator, that will be s bar divided by square root of n. So which would be s bar is 1.8 divided by the square root of 50. So which comes out to be 0.25. So now if I actually find the t-stat, that would be the numerator divided by the denominator. So we get this large number. So we get it to be negative 7.46. Now, if I were to go back here to see where it would land, I would find that this number would be way out here somewhere. So if my number 13.4, I keep on forgetting the number, I think it was 13.4, yes, 13.4 were the true population mean, then getting a number as low as 11.5 would be very, very low. So we would then in this case, say that it's probably not right that this is the mean any longer. So we would say we reject the null. And the way we would say it, well, is the t-stat is minus 7.46, which is lower than the critical value of t, which is 2.00. Or we could actually write absolute value of t-stat is, and then we can delete the negative sign, because sometimes if it's lower, sometimes maybe above. So just to keep it easier, let's just take the absolute value is, which is, then we would say higher. And we always write this sentence. So the absolute value of t stat is 7.46, which is higher than the critical value of t. So then we would say we therefore reject the null. The population mean may not be 13.4 seconds. So we then say that this null is rejected. We may say that some people, we are always really inclined to saying that the alternate hypothesis is true, but that's a wrong statement. We always say we either reject the null or not reject the null. Now, if you notice here, what we did is, since we said changed, this was, the alternate was not equal to, so therefore we put in two values here. This is called a two-tailed test, because if I again go here, if I were to draw a nice distribution to show it, we were showing that this is the mu. If we go anywhere to the left or to the right, then we would reject the null. So therefore, if I land in any of the two tails, that would be a bad thing. That would mean that we reject the null. So therefore, this kind of distribution where we did this study is called a two-tailed test. And we just did a two-tailed test where the population standard deviation is not known, then we would follow these steps. Now, what if the population standard deviation was known? So let's say that maybe we did all this work. Let's try this example again. And the mean is 13.4 seconds with standard deviation at 1 point, or let's say 2.4 seconds, okay? So in that case, now we have the average population mean and the population mean and the population standard deviation. So we have our mu and we have our sigma. And here we also have our x bar and our mu. Or sorry, we have s bar. So in our case, if I were to follow all the steps, so if the population standard deviation was known, the first step, step 1, it is the same as before. So I would write the null and alternate hypothesis just like before. I will just copy this over and bring it over here. And then collecting the data, we still have the data collected, so which is nice. Now, in the third part, we are now going to, so step 2, yes, we collected the data. Now in step 3, we now have to do the test. Now, since we have the population standard deviation, which is this number, we are going to use the z-value or the z-statistic. So instead of here where we were talking about we have 95% of the time we have these values, we can now find the z-values for those 95% of the time. So we could plug in those values here. And what we could say is equals to, the z-values would be norm dot inv. Actually, we can try norm dot s dot inv. The probability would be 0.05 divided by 2. And so we say it is 1.959. And this is assuming we are testing that we're doing a 95% test. So this number would be, we're saying that 95% of the time, if I took a sample, it should lie between this number or the other side of the number. These are the two limits. And so we would find, in our case, the z-values. And the way we calculate the z-values is using this formula. So this would be my z-values, or z-stat. So again, I would do the numerator and the denominator. So for the numerator, I would look at the numbers x bar, which is 11.5. So it will be 11.5 minus 13.4. And so we find that to be negative 1.9. And the denominator will be, now instead of using the sample standard deviation, which was 1.8 seconds, I will use the population standard deviation, which is 2.4 seconds, which we have calculated, or which was given right up here. So the denominator is going to be 2.4 divided by the square root of n, which is 50. And then we would find the z-stat, which would be the numerator divided by the denominator. And it comes up to be 5.59. So then we would say that when our interpretation would be the same thing, it would be the absolute value of z is greater than we would call it the critical value, which is, in our case, 1.96. As we calculated before, right here, 1.959 or 1.96. So we can therefore reject the null. So we would then say that yes, definitely the null is, we rejected because it seems very unlikely that the population mean is still at 13.4 seconds. Now, before we move on, again, we were talking about the population standard deviation is known or unknown. If it's known, we use the normal distribution. If it's unknown, we use the t-distribution. We use 95% as our level. So whenever we calculated our thresholds, we did it at 95% of the time. But we have two other thresholds that we could use, which is 90% or 99%. So in our case, in the question, it may say test at 95% or at 99% or at 90%. In another video, we are going to look at how to evaluate our hypothesis, mainly our null and alternate hypothesis, at different critical values, mainly the 10% and the 1% critical values. Hope you have a good day, and I will see you at a later video. Goodbye.